Okay, hi everybody. So in this video, I want to introduce a new proof technique called proof by contradiction. So to take a look at our first example, let's just first make sure we define carefully what it means for a number to be rational. So we say a real number x is rational if we can write it as a quotient, a fraction of two integers a and b, where we assume that the denominator b is non-zero so that this fraction is defined. And if x is not a rational number, then we say it is irrational. So we define irrational by saying it are numbers that are not rational. So it kind of gets defined by here's a property that it doesn't satisfy. Okay, and using this definition, let's consider the following proposition. The number square root of 2 is irrational. So this is something that we all probably are aware is true. But how could we prove this? Well, let's consider how we might get something like this going. So maybe we can say, let's suppose that the square root of 2 is irrational. But we can't begin our proof by supposing the thing that we're trying to prove. So where do we get started? Just by saying the only given information we have here is that we're considering square root of 2. So it's not clear how to do this directly. So let's investigate a new proof technique called proof by contradiction. So let's lay out the logic for how proof by contradiction is going to work. But first, just be aware that this is often useful to do, like in the previous case, where we have no idea how to get started. So direct proof really isn't going to work in those scenarios. So the logic behind proof by contradiction is, well, if we want to prove that some statement P is true, an alternate way of doing this is by showing that its negation is false. Because remember, P and its negation have the exact opposite truth values. So if the negation of P is false, then we know it must follow that P is true. So proof by contradiction is going to set out to hopefully prove that not P is false. And so here's how we can prove a statement being false. So here's an outline for proof by contradiction, is that we suppose that the negation of the statement we're trying to prove. And then based on that assumption, we go through a series of arguments that hopefully get us to arrive at some contradiction, that some statement is both true and false at the same time. And once we realize that our initial assumption leads to a contradiction, therefore that original assumption, the negation of P, is false, and thus the original statement we were trying to prove P is true. So in this video, I want to just focus on how we would get these sorts of proofs started, and we'll work out the details together in class. So let's say, for example, we want to prove this proposition that the number square root of 2 is irrational, and we're going to do this by contradiction. So here's our statement P, and it might be useful to just write out what the negation of this is. And the negation of this would be that the number square root of 2 is not irrational, which is more clearly stated as the number 2 is rational. Okay, and so clearly if one of these is true, then the other one has to be false, and vice versa. So we're going to try and prove that the negation, for example, of P is false. And so using this method of proof by contradiction, our proof is going to start by supposing the negation of this statement. So we're going to suppose that not P is true. So suppose that square root of 2 is rational. And this is a nicer way to start here because we actually have a definition for what it means to be rational. So then we can start by writing out what is the definition of rational, and then you might think about where you're heading from here to ultimately get some contradiction. But we'll look at this exact proof together in class. I just want to make sure it's clear how and why we would start it this way if we were using contradiction. And oftentimes we want to prove statements that involve quantifiers, there exists, and for all. So it's going to be useful to review how we can negate statements that have quantifiers, because if we want to prove a statement that has quantifiers in it by contradiction, the first step would be to negate that statement. So I'll go through one here. We did talk about these in class, so you might want to check out the worksheet that we did, worksheet 3 on quantifiers. But let's say we want to prove the following statement: there exists no integers a and b for which 18a plus 6b is equal to 1. And so if I want to prove this by contradiction, I would want to start by supposing not p. So how do we even figure out what this negation of p is? So these are where the symbols might come in handy. So we can restate this actually as a for all statement. So for any pairs of integers a and b, it is not possible that 18a plus 6b is equal to 1. So this is logically equivalent to the statement that we started with, right? Since saying that there are no two integers for which when we combine them in this way we get 1, it's the same thing as saying that for any two integers a and b, when we combine them in this way, we don't get 1. And lastly, let's state this original statement using quantifiers. And I apologize, I have a typo here. So when we say for any two integers a and b, right, this is our for all a and b in z. Sorry, I typed out the word in. So when we use the quantifier for all, eventually when we negate this, it should use the quantifier there exists. But our original statement is equivalent to saying for all integers a and b, 18a plus 6b is not equal to 1. And so now when we negate this statement, you may recall that we're going to change the for all quantifier to a there exists quantifier, and then we negate the statement. So if we have for all a and b in z, 18a plus 6b is not equal to 1, the negation of this would change this to there exists integers a and b such that 18a plus 6b does indeed equal 1. And this is going to be useful since if I wanted to prove a proposition such as this one using proof by contradiction, then realizing what the negation of p is gives us the start to our proof. So the proof of this proposition by contradiction would begin by supposing the negation. So in this case, we would suppose there are integers a and b such that 18a plus 6b is equal to 1. And then from there, we hope to arrive at a contradiction. But that's what the first step of that proof would involve, and that is involving negating a quantifier. So just recall how you negate for all statements and how you negate there exist statements. So those are going to be a couple of questions on the reading quiz. And lastly, I want to talk about how we negate conditional statements, since we can use proof by contradiction to prove if-then statements, just like we did direct proof and contrapositive proof. So in order to do so, we would need to negate the initial conditional statement. So you may recall that the negation of a conditional statement, so saying not if P then Q, actually results in an and statement. So the only way this conditional statement is false is if the hypothesis is true and the conclusion is not true. And so here's, using the truth table, we can verify that P implies Q and P and not Q are negations of each other because they have the exact opposite truth values. And if you have any questions or don't recall this, want some extra practice, this we did on worksheet 2 in class together. And so to take a look at a couple of examples, let's say we have the following conditional statement down here. If it is raining, then I will bring my umbrella to the office. What would the negation of this look like? It would be P and not Q. So in this case, it would be that the hypothesis, it is raining, is true, and the conclusion is false. So this would be, it is raining, and I did not bring my umbrella to the office. If we were negating statements such as, if a real function f is differentiable, then it is continuous. Well, for that one, we would say a function satisfies the hypothesis but doesn't satisfy the conclusion. So in that case, it would be f is differentiable but not continuous. And so to just state the general outline for how you prove conditional statements by contradiction, it's not any different than how we started. We suppose the opposite, we suppose the negation of what we're trying to prove, and then hope to get a contradiction. So if we're trying to prove if P then Q, then what we just recalled is we would start by supposing the negation that P is true and not Q is true. And then we use a series of logical arguments to hopefully arrive at some contradiction that some statement, we'll just call it C, is true and false, which can't be the case. So therefore, our original assumption was false, which is logically equivalent to saying the original statement is true. So we're not redefining proof by contradiction. We're just being a little bit careful with how we start our proof, how we negate the original conditional statement. So to take a look at an example, and maybe the actual proof here is beyond the scope of what we're doing in class, but just to get a feel for how these proofs look, let's say we wanted to prove the previous statement. If a real function f is differentiable, then it is continuous. So this proof, as we just went over on the previous slide, we would start by supposing the negation of this, which is f of x is real valued function that is differentiable. So this is true, but the conclusion is not true. So we're going to suppose we have a function that's differentiable, but not continuous. So then we can start by stating what we just assumed. So if we assume f is differentiable, then we know that this limit of this difference quotient has to exist. And looking at this quotient, we could use properties of limits that you may recall from calculus that says we can break this up. And now if this limit exists, the only way this could exist, notice on the bottom, this limit approaches 0. So the only way a limit which has a 0 in the denominator exists is if the limit in the numerator also approaches 0. So now we can conclude that the limit as x goes to a has to be 0 also. So this is saying that the numerator of this also must approach 0. And so if this limit equals 0, that's equivalent to saying that the limit of f of x as x goes to a minus the value of the function at a is equal to 0, just using properties of limits again. So that leads us to the limit as x approaches a of f of x has to equal f of a. That's the only way that we would get a 0 in the numerator, and that's the only way this limit exists, which we know it must. Okay, so now let's consider the other assumption, which is that f of x is not continuous. And so if that is the case, then we know that there has to be some value a in its domain such that the limit as x approaches a of f doesn't equal f of a, because this is what it means by definition. To be continuous would be the equal sign here. So there has to be at least one point where this is not true. But notice over here, we just said that this, in order for the derivative to exist, in order for this limit to exist, that this limit has to equal f of a. So there's our contradiction. Over here, we've got that the limit equals a. Over here, we see that the limit does not equal f of a, and we've got our contradiction. So it might be nice to just explain to the reader what just happened, and then to summarize that since we just showed that the negation of the original statement is false, therefore we know the original statement must be true. So the mathematics here is probably beyond the scope of what we're worrying about in class, but I just wanted to walk through this proof informally just to give you a feel for how proof by contradiction works. We'll go through plenty of examples in class this week. Okay, see you in class.